80,000 tons of steel and cargo pushing through heavy ocean swells. The physical mass of our global transport systems is staggering. Decarbonizing machines like this exposes a difficult gap. While the world is aggressively shifting toward electricity, we cannot physically or economically replace every combustion engine with a battery. Synthetic fuels function as specialized engineered tools reserved for the most stubborn decarbonization challenges. They solve for specific physical limits that electricity cannot yet reach. For corporate planners and investors, this creates a specific choice. You have to decide when to scrap existing infrastructure for a new electrical system and when to pay the high market premium for a drop-in synthetic fuel. This 9-point scorecard maps synthetic fuel viability. It begins with physics. Is electrification difficult and energy density critical? Next, financials. The value of existing infrastructure and if the product commands a premium. Finally, access to resources, long-duration storage value, and dual-mode flexibility. We are going to map these exact conditions directly to specific industries. This creates a framework to see where the math works and where the synthetic fuel premium is earned. Miscalculating these variables leads to significant capital waste. Synthetic fuels only make sense when the cost of replacing physical hardware is higher than the cost of manufacturing the fuel itself. To see this in practice, we look at the sky and the open ocean, environments where physics dictates our energy choices. This decision tree starts with a decarbonization mandate, which immediately leads to the first question: is extreme energy density critical, and is electrification difficult? If you try to power a commercial airliner or a long-haul cargo ship with batteries, the weight becomes the obstacle. The battery mass required to cross the Pacific prevents the ship from carrying actual cargo. Because of that physical limit, the path follows the yes route. Operators rely on liquid drop-in replacements like sustainable aviation fuel or SAF and marine e-methanol. The sector avoids grounding its fleet, but it must absorb the high cost of manufacturing these specialized fuels. That production cost flows directly downstream, resulting in more expensive flight tickets and elevated global shipping rates. For these heavy transport operators, the trade-off is a physical requirement. They lack alternative technologies capable of moving that much mass across those distances. In aviation and maritime transport, energy density dictates survival. Paying the synthetic fuel premium is the only way to keep global trade moving while meeting emissions targets. On land, the constraints shift toward heavy industry, which is often anchored by decades of steel and iron infrastructure. Our framework moves to the second trigger: sectors relying on high-value existing assets that cannot be easily replaced. This creates a financial choice between capital expenditure, the upfront cost to build a new system, and operational expenditure, the daily cost to run it. This logic applies to sovereign defense fleets requiring synthetic diesel and oil refineries integrating synthetic crude into existing systems. Using drop-in synthetic fuels saves billions in upfront capital. It allows current combustion engines, pipelines, and processing tanks to stay operational without modification. However, avoiding that initial upgrade locks the operator into high ongoing costs to secure the fuel supply. For defense and heavy industry, synthetic fuels act as a financial shock absorber. They buy time and preserve the value of physical assets that would otherwise be abandoned. We also have to consider national grid stability and chemical supply chains. In these sectors, reliability often outweighs pure energy efficiency. This brings us to the final triggers: severe regulatory mandates, the need for energy security, and seasonal storage requirements. When it comes to long-duration seasonal storage, synthetic methane is the primary example. Creating synthetic methane involves complex chemical conversions that result in a significant loss of the initial energy. Nations accept this loss because it guarantees dispatchable fuel exactly when and where the grid needs it, satisfying national security requirements. The final node is market flexibility. Producing renewable methanol or green hydrocarbons allows a facility to pivot between fuel markets and specialty chemical markets. While this complicates logistics, it lowers investment risk by allowing producers to chase the highest market premium available. When national security or strict compliance is the priority, the inefficiency of producing synthetic fuels becomes a necessary insurance policy. Stepping back from these individual trees reveals a strategic overview of the entire energy landscape. This quadrant chart plots infrastructure value against the difficulty of direct electrification. The most viable cases, SAF, marine e-methanol, and synthetic diesel, sit in the top right quadrant. Conversely, the bottom left contains passenger transport and residential heating. Here, direct electrification is already the efficient choice. For the capital allocator, the map is clear. Target portfolios weighted toward heavy transport and seasonal grid storage, and avoid consumer-level synthetic fuel hype. For the corporate pragmatist, use synthetic fuels to safeguard legacy assets and achieve immediate compliance while you bridge toward future technologies. The baseline rule remains: avoid the cost of manufacturing a synthesized liquid fuel if a standard battery can physically do the job. Ultimately, these fuels represent a strategic stronghold, a necessary choice for the industries that are physically too heavy, financially too expensive, or too critical to function on electricity alone.